Okay, so it's been a week, but where we left things last Wednesday, we were working with sampling distributions. We were on worksheet 11. We got through a lot of that material. So I want to start today finishing up the last page of that. And then I'm talking about permutation distributions. No, excuse me, bootstrap resampling, which you guys read about, and talk about how we can use those to construct confidence intervals. So as far as work for the week goes, you've got a homework assignment due tonight, and that is going to be submitted with our markdown. And then you've got your next homework assignment will be due the following Wednesday. So nothing due on Monday other than you'll have a reading quiz before Monday's class. Any questions before we get started today? Okay, so let's kind of think about the following example. So let's say here we are, question 9 on worksheet 11. So this is a familiar problem that we've seen before, at least part A. So I want to talk about how the essential limit theorem might fit into a problem like this. So the situation here is, let's just say we're flipping a coin 10 times. And we're going to count the number of flips that land on heads. And that would be binomial distribution, where we have 10 trials. We'll assume the coin is fair, so the probability of a head is 1/2. And that's what's more or less plotted in the histogram below. And so if we want to calculate what is the probability that we would get somewhere between 3 or 4 heads, right? Since here we can only get an integer number for the number of heads, then we could use R, for example. We could do this in a different number of ways, right? But that's going to calculate the probability of getting exactly 3 heads. So it's going to add up all of those. And then we could also take into account what are the odds of getting exactly 4 heads. Sorry, I think I shaded in 4 before. So that would be the 3 and the 4 shaded in right there. So we could calculate this in R. And if you've got a terminal open, you can verify that this should come out to 0.3223. So in other words, from the binomial distribution, we would get that there's about a 32% chance that we would get exactly 3 or 4 heads. Any questions about that? And so we can use the normal distribution to come up with an approximation for this binomial distribution. So it looks approximately normal. It's just a little boxed off. And so we could actually fit a normal curve to a binomial distribution. We just need to identify the mean and the standard deviation. So in this case, the mean for a binomial distribution would be n times p, which is 5. And we can calculate the variance of this distribution. So we're going to construct a normal distribution. And the idea is we're going to use the mean and the standard deviation from the binomial distribution to describe the spread and center of the corresponding approximate normal distribution. So the mean we get by n times p. The standard deviation we can get by calculating the variance, which is n times p times q. So that would be 10 times 0.5 times 1 minus 0.5. That comes out to 2.5. So we could approximate this binomial distribution up top using a normal distribution with a mean of 5 and a standard deviation that is the square root of 2.5, since right, what we found was the variance, excuse me. Any questions? So all we're doing is saying that let's find the mean and the standard deviation of the binomial distribution, use those parameters to approximate the binomial distribution with a smooth curve for the normal distribution. And then we could use this normal distribution to calculate this by saying, let's take p norm of 4 and subtract p norm of 3. So what that would do is it's going to calculate the area right beneath the normal distribution over the interval from 3 to 4. So it's going to calculate this green area over here. And that comes out to approximately 0.161. Any questions so far? Okay, thank you. And so we can see by comparing these two values, this is the exact value. So this is literally the probability that that would happen. If we use a normal distribution to approximate this, it's about like, it's not even close, right? It's about half off from up top. And hopefully it seems reasonable that our answer is too small because we're missing some area. So the problem here is we're trying to approximate something which is discrete, like how many heads do you get with a distribution which is continuous. So and this will come up at other points in the semester, there is a way to correct for this underestimate that we're going to get with when we use a normal distribution approximation. And so that's what's called the continuity correction. And what we do is, instead of putting in 3 for the lower limit, we go half a unit below that. So we go to 2.5. And I guess whether or not we include these or exclude them, it's kind of a moot point when we're working with a normal distribution. And then we go half a unit above the upper value. So that was 4. So then we go up to 4.5. So the idea here is that we're going to extend our region a little bit to include a little bit of extra area to account for that area. And that little extra red area that we now captured by going these half a units above and below is going to match up that missing gray block of area that we had initially. So kind of the steps here would be, you know, if we know the values for some random variable, which is given by a binomial distribution, find the mean and the standard deviation using our shortcuts for binomial distributions. We can approximate x with the normal distribution. And then we approximate it again by going half a unit above and below our original limits. So a better approximation would have been to take this original formula that we had and change those values to 4.5 and 3.5. Sorry. And then when we run that in R, that comes out to 3190. And you can see that that gives us a much better match to the 32% that we got when we did the exact calculation. So I'll just say sometimes we approximate binomial things with continuous distributions with a normal distribution, and you know, the reason why we do that is we have nice ways of working with normal distributions, and when we use that normal distribution for an approximation, we should build in this correction for the fact that we're using a continuous distribution to approximate a discrete random variable. Yeah, there's a question.
Oh no, I think you meant to put 2.5 on that second P norm.
Yes, I did. Thank you. Yes, that's exactly right. We go half a unit below. Thank you, Stephanie. Yeah. Yes, and that comes out to the 0.3190. Yeah. Okay, then that's a wrap for chapter 4, which was dealing with sampling distribution. So for the homework, which is going to be due next week, you've got some problems that ask you to use the central limit theorem for a mean, for a proportion. You've got a problem which is pretty similar to the one we worked on last time, where we're going to kind of work out a sampling distribution for another statistic like x max or x min. And then we've done lots of simulations of these things using permutation distributions and other things. So your homework is going to have you set up sampling distributions using all three of these different methods. Some of it will be in R, some of it you'll be writing on paper. But I am going to ask for your next homework assignment again to be in R Markdown. I'll give you a template to work with again, and for that one, the instructions are going to be to create a PDF for next time instead of an HTML document. And let's see how that goes in. So I want you to upload the R Markdown file along with, when you knit it to a PDF. Any questions? Okay. So then let's take a look at the material in chapter 5. So chapter 5 is going to kind of talk about the other main type of inference that we do, which is using confidence intervals. So kind of the main forms of statistical inference, like taking a sample, trying to infer something about a population. Those sorts of questions are usually grouped into things like when there's a claim about the value of the population parameter and we want to test that claim, we would use a statistical test. In other situations, there's no claim about the value, so we might just ask, like, what is the mean weight of newborns in North Carolina without any preconceived notion about what that might be. And so that's where we would use confidence intervals to come up with intervals of plausible values for the unknown population parameter. So the example that you guys read about dealt with this data set for North Carolina births in 2004. And so the question might be, you know, and if we want to be careful that we're not kind of biasing things, then our sample came from people that were born in North Carolina in 2004. So that's what we should kind of restrict our notion of population to. And so for a question like this, there's no claim about what that value should be. So we're not like gauging two competing claims. We just want to estimate the value. So the kind of starting point would be, let's calculate the corresponding statistic. So this starting point is what we would call a point estimate. So we would take the corresponding mean from the sample, right? That seems like the best guess that you would have from that. And again, we call that a point estimate because we're estimating that with just one value. But what we've seen with sampling distributions is, yeah, we would expect these values to be close to the population parameter, but they're going to vary from sample to sample. Different samples are going to have different newborns included in them. So there is going to be some error that is due to the variability in sampling. So the question is, how can we measure that variability, the standard error, when we only have one sample? So we can't create a sampling distribution from a population because we don't have access to everybody in the population. So in order to work around that, we're going to set up what's called a bootstrap distribution. And these are pretty similar to permutation distributions, but there's a big distinction that we want to be sure we make with them. So as with permutation tests, we'll see different types of bootstrapping depending on what it is that we're trying to estimate. So we'll start by trying to estimate one population parameter, like the mean births of the mean birth weight of babies in North Carolina. Then we'll think about how we can come up with an estimate for a difference in two. Sorry, that would be a difference in two parameters. Like, is the mean of this different from the mean of that? And then we'll talk about what to do with matched pairs. And so the kind of philosophy about what we're doing and why we're doing it is going to be the same in these situations, but like how we execute it is going to have to be a little bit different depending on whether things are matched or not matched and so on. So just be careful that you know, these problems are done differently depending on what it is you're trying to estimate. So you want to think about that first before you jump into how are we going to create bootstrap samples. So when we're dealing, which is what this first one is asking, with one population parameter, then that means we just have one sample, right? Like all 1,000 some odd babies that we have in this sample. So we have one sample, it has size n, and we're just going to draw from that original sample with replacement. And we're going to draw the same number of values that we had in the original sample. So we're just going to pick, if in this case, our sample had 1,009 babies, all with different weights, we're going to just pick 1,009 different weights from our sample with replacement. And we repeat that many, many times. So we'll get R to kind of do a for loop and repeat this for us. And then we look at the corresponding distribution of all of these statistics from each of those bootstrap resamples. So this was kind of relating to the reading quiz. So this was the one that was in the video, and you had a similar one on the quiz. So were there any questions about what sort of properties we're looking for when we're generating bootstrap resamples? Okay, so yeah, we might get, one repeated value every single time. It's possible that we get the original sample back as a bootstrap resample. We can't get samples with less things, we can't get samples with more things, and we can't get samples that have values that weren't in the original sample. But again, we are picking with replacement. So it's like these 4 values are in a bag, we shake it up, we pick a value, and then we put it back in the bag, we shake it up, and then it's possible we pick it again. So one thing that you should be thinking about is we're going to write some R code to do this. It's going to use that sample command. We've been oftentimes setting the replace equals false when we're doing permutation samples. Here, we're going to want that to be true. We're going to want to pick with replacement. And just kind of thinking about, how many possible bootstrap resamples there are, it's complicated. I'll just say that. So you might want to say, okay, if I had a sample of 4 things over here, you might think that, okay, for the first choice, I can pick any one of those 4 things. And for the second choice, I can pick any one of those 4 things. And the third and the fourth. So if you do that calculation, you're saying, okay, I can pick any one of 4 things in any one of those 4 spots. That gives me 256 possible samples. But this is not how the calculation goes. Since that ignores that ordering does not matter. So that treats, this sample over here the same as if it were picked in the exact opposite way. So we'd want to treat these 2 samples the same, even though they were picked in different way. So I'll just say it's really complicated to make sure that you're not double counting things and paying attention to the ordering of this. So in fact, in this case, we have a lot less. There's, I think, there's less than 100 permutation resamples bootstrap resamples that we could have here. But there is a formula to calculate exactly how many there are based on how large your original sample is. If you're kind of curious about that combinatorics argument, I'll just point you to the exercise in the book. That is not homework, but that's something optional if you want to think about that. Okay, so the goal here is we want to approximate one population parameter. And so we have one sample, we calculate the mean of that sample. That's going to be our starting point for our estimate. Yeah, sorry, I'm getting a suggestion about the formula. I will, whoever chatted that in, when I've got a moment, I will respond to that. It is a choose formula, n choose k type of formula, but it's a little bit complicated where that comes from. Okay, so we have our starting point, and then the whole point here is we don't want to be so arrogant to say like our sample is perfect, so the mean weight for all babies is going to exactly equal what I got in my sample. We should build in some margin of error into this estimate. And so one way to do it is bootstrapping. Really powerful way to do this. So here is the code for this, and I'll just say I am working with a file. You might want to, for the rest of the class, we'll be doing stuff in R Markdown. So if it's useful for you to look at this stuff, to be able to work with it in R, there is a file called 12 bootstrap part 1.rmd, which is up in Canvas. So I'll be opening that and working with that in a second. So here's the code to generate this bootstrap distribution over here. So kind of the first thing we want to do is call in our data, right? Library resample. And then it seems to start off pretty similar to permutation resamples. And I think I missed part of the code that I would have had entered when we calculated on this up here, but that's okay. Yeah, this has a typo over here. So let me open up the file actually, since I have the code in there. We can kind of hash it out in there. Okay, is this can you guys, is the text big enough or you want me to zoom in? Oh, it's good. Okay. So yeah, so this was kind of, I don't think I did this yet. Did I load the data set? I did. Okay, so that would be done. So first was saying, well, what would a good estimate be? And that would be the mean of NC.
You forgot the R in the Kirby bracket.
Oh, thank you. Yes, that was on purpose, just making sure you're paying attention. Thanks. NCE births 2004, the variable was weight. And so that was that calculation. Great. And that's where the 3,448 grams came from. Okay, so now we want to come down and run bootstrap samples. So yeah, so here's what we had before. I was kind of missing some of this stuff over here. So then what I want to do is set up a vector of my sample data, because right now it's just living in that big data set. And I don't need to subset or partition the data set or filter anything out. I want all of the birth weights that were in that sample. So that's what this does over here. So now if I were to view weight, it would just be a vector without any header that just has all of these weights. You don't need to do this command. You could view the data and look at how many observations there are, but that really isn't necessary. So this command length will go into the vector weight and count how many observations are in that vector. So in this case, that should come out to 1,009 because that's how many observations we have. That's a really useful operation. How many things are in this vector? All right, so now we want to do the bootstrapping. So we're going to create a for loop, and here we're going to do 10 to the 5th. We don't need to do the +1, adjust things over here. We're just going to generate 100,000 samples in this case. And what we're going to sample from is we're going to go into the vector weight, right? So this is like the bag of all of our all of the observations that we have. And then we're going to shuffle it up and we're going to pick this many values from weight, okay, where again, total is 1,009. And if I had replace equals false over here, that would give me back the original sample, right? I would pick the 1009 values that were already there. So it's the setting this replace equal to true that really is bootstrapping here. Each time I pick one of these values, I put it back into the sample, and then I pick again. And then once we get that sample, we calculate its mean, we store the mean over here, and then we plot it. So really the meat of it is in this loop over here. And really the main thing that we changed was our sampling process. Sorry, my computer is a little slow today, but here's the bootstrap distribution. So this is not a sampling distribution, but it's using a bootstrap distribution to approximate the sampling distribution. Any questions about that? So this would be like the simplest of the cases. When we only have one sample, we're not comparing different things. We don't have to subset data, all of that. Okay, great. Let's see. Okay, yeah, and so that's where this code came from. So I did a little bit different than it was listed over here. This was using like the index type of method where we pick a bunch of random numbers, we assign them to index, and then we pick those random numbers out of the original vector. It's another way to do it. It's a little bit different than how it's done in Markdown. Okay, and so this these last two lines, sorry, that I had in our Markdown, which are typed down here, which were the mean and the standard deviation of the result, are telling us the center of the bootstrap distribution, and it's approximating the standard error, right? The standard deviation is going to tell us the kind of standard error of the bootstrap estimate for the sampling distribution. And if you ran this on your computer, you probably got different values. And that's okay. There's going to be randomness involved there. And in fact, if you all get the same values, then that would be really odd. So there should be some degree of variability here. Okay, so any questions about how we got that first bootstrap distribution? Okay, so I just want to kind of talk about, we've got different things going on here. So we have a sample, we have a population, and we have some bootstrapping. Let me mark this up. Sorry, it's always fun when I switch things, and sometimes if you're the last person to speak, then you get the camera. So when we're doing this process, right, typically this is what we don't know. We don't know like what shape the population is, what the mean is, what the standard deviation is, or any of that stuff. Instead, we have one sample. So this is kind of what we're given. And so the idea is, if we had the population, we've talked about how we can use the central limit theorem to figure out exactly what the sampling distribution would look like. So this is the exact sampling distribution. I think here the sample size was 50. So that I just calculated using the central limit theorem. And down below, we have what would be the bootstrap distribution that would be generated, or a bootstrap distribution generated from this sample. And the idea is, before we use bootstrap distributions for these estimates, it would be good to know how good does this match up with what we should get precisely from for the sampling distribution from the central limit theorem. So I just did this. I'm going to do like a proof by example here, just to kind of look at what happened in this example when we compare the sample and the population. We can see that they're pretty close to each other. Okay, although our sample is not particularly normal in this case, but it's a little bit normal. But they have the same mean, sort of. They have a close standard deviation, but not exactly the same. And similarly, so if the population and the sample pretty much are resembling each other, then when we create sampling distributions from each of them, we should get things that are pretty close to each other. So when we look at the sampling distribution, so the bootstrap estimate is pretty close. And if we actually look at it, you can see that the standard error, which is really what we want to get, that's the missing ingredient, is we want to know like how much variability is there in our estimate. These are really close. The means are off a little bit. So we actually have a better estimate for the standard error than we have for the mean. So the bootstrap distribution is not exactly the sampling distribution, but it's a pretty good estimate for it. Any questions? Okay, so let's just kind of summarize what we've talked about. So so that we're talking about section 5.2. So the plug-in principle is basically just saying, if we want to estimate the parameter, our point estimate should be the sample statistic. And so on, right? So anytime we have a population parameter that we don't know its value, but we've collected a random sample, our starting point would be, let's calculate the corresponding statistic for that sample. This goes on for all. So if we wanted to estimate the variance, we would take a sample and calculate the variance of the sample. So we're going to start with our estimate for the parameter with this statistic, and then we're going to build in some error into that estimate using bootstrapping. Okay, so let's think about another example, which is with a data set called Bangladesh. So I'm going to open up, I'm going to move back into R Markdown. Okay, so this data set, Bangladesh, it has like 271 observations in it. And so you've got a homework problem that you're going to work on for next week's assignment that also deals with this data set. We're going to deal with cobalt levels on homework. This problem is asking us about arsenic levels in groundwater samples from Bangladesh. And what we want to do is come up with an approximation, say, for the arsenic level of all groundwater in Bangladesh. So first thing to do is let's just kind of consider what our sample looks like. So if I want to calculate, why don't you guys go ahead and calculate the mean and standard deviation of this data set if you've got R open. And I want to make sure that things are going okay with everyone. So if you just chat me the sample mean for the arsenic level, for example, just to make sure people are going about this okay. Okay, thanks for answers that are coming in. Okay, good. So this all seems to be going well. That's right. So you're just going to use the mean and standard deviation functions. And here the data set is Bangladesh. And the variable is arsenic. I'm just going to save these values as well. Maybe I'll mute them. I won't see any output here because I assigned them to these values over here. But yeah, the mean is about 125 parts per billion, and the standard deviation is like 298. Yeah. Okay, and so if I wanted to see the sample values, then what I could do is just plot it. I forgot that I'm in R Markdown and not in R. Okay, so there's our histogram. The sample here is highly not normal, right? Very, very skewed. This is good, right? You would want to see that arsenic levels are very low in almost all of the samples. It would be quite concerning. These outliers are extremely high. So it's possible these outliers were error, data entry error. Someone missed a decimal point. That stuff happens all the time, unfortunately. Or they could be a result of just some areas where water is extremely high in arsenic. Okay, so this is kind of telling us information about our sample. So we see our sample is skewed. We've got a mean and standard deviation for the sample. And so now we want to go in and set up bootstrap distribution. And so down here, I'm assuming that some vector called arsenic was created. I haven't created that yet. So what arsenic is, right? It's just all of those values. So I can go ahead and create this vector of arsenic values. And this is important to know. I called this total before. We can call this whatever. You can call that, like, that's how big my sample was. And for interest of most of these problems, I'll say kind of the benchmark here, we use 10 to the 5th on the previous problem, would be to use 10 to the 4th at least. So 10 to the 4th is totally fine. And now we're going to create a bootstrap distribution for the mean. So this is going to be pretty similar to what we did up here. So let me just copy all of that. Paste it down here. So what is it? What about this code do we need to adjust from the previous example?
The weight, we're not testing for weight anymore.
That's right. So what can, this is no longer needed there. What are we picking from?
We could just use the arsenic variable
That's right.
we just defined.
Right, or you might have called it something different, but we want to pick from the vector of arsenic values. And so I'll just say, like, for your homework assignment for next week, you've got our markdown file and it's got like partially completed code. So there's some points in the code where there are question marks. And so kind of your goal is going to be kind of what we're doing here, which is here's some code. It's not perfect. Tell me how to tweak it so that it fits our purpose.
Like how you did the index questions in the tablet or the template that you did, where you have the question marks in the brackets for it.
That's right. Yep. Okay, so yes, we want to change what we're picking from, and what would I put in this place over here?
Sample.in.
Yeah, so we can either type in 271, which was the number of observations, if you want to do it that way, or we could type in whatever the output of that length vector was. So that's going to tell me how many observations were in the vector arsenic. Okay, so it's going to pick all of these things. What else do I need to change here?
Are we still replacing it?
We are still replacing it. Yeah, so that's okay. We're going to pick with replacement. So I think this part is okay. We're going to pick from arsenic. We're going to pick 271 values with replacement. That gives me a bootstrap sample that I called X. I'm going to calculate the mean of that bootstrap sample. And I'm going to store it where? So result is what I used up here in this example. We call this numeric vector where we're going to store our statistics result. And again, you're welcome to choose your favorite name for that, but we want to be consistent. So I started some work up here based on what I was doing up here. I don't want result here. That's not what I called it in this case, right? What's the name of the vector where I should be storing each of these means?
Boot.mean.
Yeah. And again, you guys are welcome to call these things whatever you like. Me, that means the bootstrap distribution for the mean. You don't want to put spaces. You actually can't put spaces in when you assign things to variables. So just keep that in mind. So oftentimes we use periods to hold a space. And so I think that would work. Coming down here, we would want to not plot result, but we want to plot this new distribution that we called bootstrap mean.
Can you use underscore to represent a space, or does that then do something else with it?
You could do that. I'll just say that that's a little bit less common. Sometimes we use that for subscripts instead, and so that's why that's less common. You could type whatever you want there. You wouldn't want to put a $sign. Like there are some symbols that are reserved, and they'll usually look differently colored. So if you see something differently colored, that might be a problem. But yeah, I would say usually the convention is to put a period there. Yeah.
Great to know. Thank you.
Okay, and then we can calculate these values over here. And I will store these in what I'll call like the center of the bootstrap distribution. And over here, I'll call this the standard error of the bootstrap distribution. Okay, I think I don't need that stuff. And let's run this and see what happens. Any questions about that actually before I hit run here? These are pretty fast. So there's my bootstrap distribution. It's worth pointing out, right? Here is our sample, highly unnormal. Even with data like that, we get a bootstrap distribution and sampling distribution, which is very closely approximated with the normal distribution. And let me actually see what this output looks like. And hopefully you're trying this out on your end. And you're getting similar stuff, but not exactly the same. We should have some variability here. So what I'm seeing is that the center is 125, which is pretty close to what the center, to what the mean of the sample was. And we're getting a standard error here, which is about 18. And again, you probably got different values, but you should be getting something close to 18, at least for the bootstrap standard error. Okay, and so that's bootstrapping and how we get those distributions. So the next thing is, well, okay, how can we use them now to construct 95% confidence interval or 90% confidence interval, so on. So yeah, let me switch back for a second to the PDF. Yeah, and so just some terminology to clear up. and we kind of saw this in the previous example, is that the center of the bootstrap distribution is not particularly good at estimating the center of the sampling distribution. So this is a biased estimator. When we try and estimate the center of a bootstrap distribution, we're going to have some issues, but that's okay. I'm not going to be approximating the center of a sampling distribution with one value, but rather I'm going to build some error into that estimate. So that's why we want to build some error into this estimate. But the good news is the spread of the bootstrap distribution is really, really close to the spread of a sampling distribution. So that's good. So our variability is pretty accurate. And the shape of a bootstrap distribution is going to be accurately reflective of the shape of the actual sampling distribution. So when we're trying to estimate a distribution that has some parameter theta, so you can think about theta typically for us is like a mean or a proportion, then we call a function that we're going to use to estimate it is called an estimator. So in the arsenic example, the parameter that we were trying to estimate, that was a mean. Kind of this is what we've been saying. It's like, okay, we are going to approximate that with X bar. And if we want to get a little bit more fancy over here, we would say our parameter is theta. That's the mean of the population. Our estimator for this, right, and that gets a hat. So whenever we're estimating, we put a little angled hat on top of it. In this case, it's a function of the 271 observations that we had in the arsenic example. So this estimator is a function of the values of our sample. And so for where we're going with this next in chapter 6 is going to be more of like a functional analysis way of approximating these things. So it's going to be useful for us to kind of think about these estimators as functions of sample values, and then we'll be able to fit some curves to those samples. So in the previous example, this arsenic one, we found an estimate for the bootstrap standard error, at least I did. So that was what I got when I did standard deviation of, what did I call this? Distribution, boot mean. So we would put an angled hat over that because it's an estimate for the standard error.
When we put a hat on top of the estimates, because that's what it is, do we then not need to do the squiggly line equal sign?
So there's two different things here. Yeah. So one is like estimates and one is approximation. And these terms get used interchangeably, but they're actually a little bit different. So yeah, the fact that like I would call this an estimate because this is giving me an estimate for the exact value of the standard error. Probably I'm already approximating it, but I could say something like that. So I would use like the approximation symbol when I'm like truncating, when I'm rounding things off or something like that.
Okay.
And that's a little bit different than saying like I can approximate an exact value, and that's different than giving an estimate for that value, if that makes sense.
Yes, it does. Thank you.
Yep. Okay, so let me just sometimes we might put a subscript boot on that to denote that it's a bootstrap standard error. So I got this as 125. I'm going to round that off. And I got my sample mean for the arsenic level. I'm going to round it off to 18 parts per billion. I think this was being measured at. And so one way to come up with, if we wanted to estimate, what is an interval where 95% of all of the sample means are going to be within a certain interval of values, we can use the rule of thumb. So here, what we're looking at is a bootstrap distribution.
Are you writing right now? Because the
I
screen is
am.
frozen for me.
What am I sharing with you? I don't even know what I'm sharing.
Oh, okay. It just loaded. It was still on the estimate for the standard error screen.
Yeah, there might be a delay, sorry. But now you can see my little, yeah. So we have a center here, which is somewhere about 18. And what these are giving me, these are estimates for the mean. So these are distributions of different sample means for each bootstrap distribution. So what this is telling me is if I go like 2 times the standard error above, 2 times the standard error below, that's one way that I can find out what are the range of values that 95% of my samples are sitting between. So in this way, I could say I have a lower cutoff, which is going to correspond to this value, which is going to be the 18 minus the 2 times 125. And then I have an upper cutoff over here, which is going to be that middle 18, and then I'm going to go 2 times the standard error above. So that would give me 250 plus 18, and that would give me 250 minus 18. So that would be 232, excuse me. So this is giving me an interval of values where 95% of all of the bootstrap means are likely to be between, right? Again, we're estimating things, so there's going to be some error here. So that's one way confidence intervals are set up, because usually sampling distributions are normal. So this rule of thumb so this works if the bootstrap distribution is normal. We'll see plenty of situations where that's not necessarily the case. That seems to be pretty good approximation here, but again, we would probably want to do a quantile normal plot to see if that's a good assumption. Any questions? Okay, so more specifically, we can use quantile functions in R to calculate these if the distribution, even if it's normal or if we're not sure it's normal. So rather than use the rule of thumb, what we typically use are quantile functions to calculate these cutoffs. So for the North Carolina births example, which was back over, way back over here, this is not quite as normal, right? There seems to be a little bit of a tail over here. So for this one, we might want to be a little bit more careful than just kind of using that rule of thumb. So instead, what we're going to do is tell R to find these cutoffs in our interval for us. So find the 2.5 percentile. And so to find the 2.5 percentile, I would take my distribution, which I stored in result, and then I want to calculate, say, the 2.5 percentile of that. So there are different ways that we could do that. And one way would be to just write out what the probability is for that. So let me come back into R. So this is the Bangladesh stuff. So let's see, here were the North Carolina births. Here was the bootstrap distribution that we did for it. And now I'm going to add the command here that I want to take the quantile of result. And this is going to calculate the 0.25 quantile. And let's see. That told me that was 3,418.175. Then, and it's nice that there's a little indicator. Oh no. My mouse has given up. Here it is. There's a little indicator over here of what the percentile is on top. If you want to do them both at once, so you can do them one at a time, like this and like this. And that gives me each of them. So these would be that this is the corresponding lower cutoff over here, and this is giving me the corresponding upper cutoff over there. So is it clear where the 2.5 and the 97.5 come from? Like we want to ignore the bottom 2.5% of samples, and we're going to ignore the top 2.5% of the samples, and we're just going to focus on the middle 95%. So that's why we're finding those two specific cutoffs. This one is telling me 2.5% of the samples are less than this. This is telling me 2.5 of the sample means were greater than this. So between these two values sits the middle 95% of our samples. And if you want to do them both at once, you can do that too, if you enter them as a vector. So that would calculate them both. And when you do it like that, I don't believe you need it's telling me that I need this, so maybe I do. I don't think I need to enter that, but that'll do the same calculation. So that the only difference is it outputs them both at once here. And so what's nice to do with these histograms, like we did with permutation distributions, is to actually we were marking the location of our observed sample on those histograms. So here it might be nice to just add vertical lines. So the command for vertical line is AB line. And then I'm going to set this one to be at the lower value. So I could either type the value or type it like this. And let me just make this one red. And let me shade it and make it thick. That's all those things are doing. And let me add next one over here. And I think this should add, let me make this one blue. That's showing the cutoffs there. And in between those two lines sit 95% of the bootstrap samples that we got. So any questions about that part? And if we want to make some sense of this, so what do we do with this bootstrap confidence interval? It's giving me a range of plausible values for the unknown population parameter. So rather than say, right, that would be a little bit arrogant to say like my sample is perfect. So we want to kind of move away from that. And just say, okay, one way that I can move away from saying it equals this is to say that it's about equal to that. And this interval estimate now gives me a better way of saying about. If I just say about, I don't know, does that mean I should expect 100 grams of variation, 50 grams of variation? It's not clear. So now that we have this standard error, it gives us a way of actually saying what about means. So we can say there's a 95% chance the interval from, I'm just going to round this off. It looks like, what was it? 3, oh, here it was. Whoa. So this was 3,418 grams to 3,478 grams. Contains the actual mean value So by finding these cutoffs, it gives us a way of more specifically quantifying what about means. So now I can see about means, we've got about like 60 grams worth of variability from the lower end of our estimate to the upper end of our estimate. So in the end, this interval is giving us a range of plausible values for this population parameter that we don't know. Okay, so we'll stop here. We're out of time. So we've been working with single estimates. What we'll talk about next time will be how we deal with differences, whether they're matched pairs, and we'll also talk about differences that are not matched pairs. And then we'll also talk about how we could extend this to other statistics besides means, proportions and variances and other things. So I would definitely encourage you guys. I don't know how you're going about like your workflow with the homework, but certainly there are problems on homework that you can start doing now, and there might be some that we'll get to next time. I would definitely encourage you guys to be doing it a little bit out at a time as opposed to like doing it all in one day. So definitely get started on the homework over the weekend. I can just post an announcement as far as like, you should be able to get going on these problems, and maybe these other questions we'll cover. You should be able to get through most of it, actually. Maybe there'll just be one problem that we'll get to on Monday. Okay, well, that's it. If you have any questions, you guys are welcome to stick around. Otherwise, I'll see you all. Have a nice weekend, and I'll see you guys on Monday.